Welcome everyone, good to be with you. If any stage there's problems with audio or video, please let me know and I will try accommodate. But yeah, good to be with you here. I'm going to be doing a sort of overview talk, I suppose, on sort of weird and wonderful construction systems and how you deal with them. So often as engineers, we have these unusual systems that the client or whoever pops up with, the architect suddenly has a great idea and wants to try X. And so I've thrown together a few of these just to give a general talk on how you'd actually approach them. And I think there's things that you can learn from each of them. Timber obviously is a lot more common and yeah, so there's a lot more established principles where shipping containers less so. Ecobricks, nothing. And then, for instance, green facades are an emerging issue. So they are something that we can then just start thinking about. So first, do apologize, a little sick today, so if I cough, sorry about that. Yeah, so we've got master's and PhD programs in fire engineering and structural fire at Stellenbosch University. We've got an online distance learning based master's in fire engineering to be launched in 2024. We do research, consulting, expert witness and development work for industry. We also do short courses. We have a fire behavior course starting in about 2 weeks' time. So either as a university course, so you basically do a postgrad course as a standalone short course, or we have a 2-day module, a CPD module starting, but it's about a bit later in October. And so it's all the fundamentals of fire behavior. So it's really sort of the basics for assessing things: fire behavior, fire spread, ignition, flashover, etc. So I'll be giving you an overview of fire testing and resistance. So how do we assess these structures that we'll be looking at? And then we'll look at shipping container structures, mass timber buildings, eco-brick homes, green facades. And then there's certain things that are transferable from one to another, certain things that are not. And yes, we will have a time for questions at the end. So you're welcome to shout if you've got some questions. Now, as a very sort of quick overview of general fire behavior, whenever you've got a fire in a compartment, so in a normal kind of building where there's an enclosure, you need to have some sort of ignition event kicking things off. Then it grows as the fire spreads across materials near it. Then we get what's called flashover, which is a thermal instability, where it goes basically from a localized fire to a full room involvement, a fully developed fire. And at that stage, it's burning with maximum intensity, maximum heat. It's ventilation controlled, so it burns as fast as air can get in, and then decay starts once the fuel has been consumed. So that's kind of the basics of enclosure fires. Now, it's very difficult well, every fire is different. So you'll soon see as most of our assessments are done based on standard fires. So this is flashover. So here's a little shack, timber shack being tested. And you would have seen it suddenly goes from flames in some places to flames everywhere. And now it's run out of oxygen. So the combustion's actually occurring outside the dwelling because unburnt gases are actually escaping. And then what you see is actually ignition occurring, that you've got pyrolysis gases, gases that can ignite, combusting outside, and then you've got cool air being sucked in at the bottom. And this can happen on a much larger scale. Now, the concept you're seeing of spread becomes important later when we start considering things such as green facades and eco-bricks, where it's not just how long a material lasts, but also to what extent does it cause spread. So yeah, so here's a triple dwelling test. First one is ignited, temperatures of about 1,000 degrees Celsius measured, flame spread onto the second one ignites, and you'll actually see it ignites. Then a hot layer builds up and rapidly descends, spreads to the third one. We had about a 3-meter diameter fire wheel. So got a little slightly panicked at this stage, but hey, it burnt out quickly. Third dwellings ignite on the outside, but it slips through. So wherever there's a gap, the fire will slip through. It slips into the dwelling and it quickly then descends. You see it drop, and then the third one's on fire as well. Now, in our buildings, we're trying to prevent this in various different ways, either by making items resistant to fire. So you have fire resistance rating, the 30-minute or 60-minute rating, or non-combustibility, because fire resistance and fire spread are two separate things. So you've got reaction to fire tests and fire resistance. So if you have a big test, what you're ultimately trying to do is make sure something like this doesn't occur, where you've got what's called compartmentation loss, where there is then multiple areas being affected at once. And when something like this occurs, this is actually a violation of the National Building Act, because our National Building Act, I think it's Act 103 or 105 of 1977, states that basically the spread of fire and smoke should be limited throughout a building. So when there has been a spread throughout a building, it actually is a violation of the Act, not a code requirement, but an Act requirement. So it's actually an obligatory requirement for buildings. And at this stage, when it gets to the stage, you probably have to demolish. But now we get then new weird and wonderful systems, and how do we start evaluating these? So normally what we evaluate systems against is the standard fire, where what we use is this red curve. So it's cynically, it's based upon kind of the rate a couple of guys could shovel coal into a furnace, but it's a semi-arbitrary, that red line. It's useful, but it's semi-arbitrary. It follows a curve and it gradually increases. So it's different to a real fire. But the way we assess products is we put them in a furnace and we build them. So apologies if you've seen this before. I just need to get everyone on the same page. So if you've got a door, a wall, a column, whatever it is, you basically put it in a big box and you expose it to heat. And you have burners, gas or diesel burners, and they will then emit. And what you have is it heats up the box, and then your sample will get exposed to fire for a certain level of times. Failure can be in various ways: emitting large amounts of smoke, burning through, collapse, etc., etc. So this is a fire resistance rating. Now, one thing that's key to remember at this stage is a fire resistance rating is how long does something resist fire? If it turns into a banana, if it breaks, etc., it doesn't have a fire resistance rating. But a combustible item can have a fire resistance rating. So if you have solid timber, it can have a fire resistance rating. It takes a period of time to burn through, and you kind of get failure when it's burned through. So a solid piece of timber can have a fire resistance rating. It may increase your fire risk. So a solid timber building will have a fire risk because the fire will be more intense and more severe. But you stay on the same time temperature curve when you test something. So even if you are testing a combustible item, all that happens is the burners just fire at a lower rate. So you control them, so you throttle them back. So now you need less diesel. So you thought you needed 50 liters of diesel. Now you only need 40 liters of diesel to power it, because the other 10 liters of equivalent diesel for your burners come from the door that's burning. It doesn't change this curve. You throttle your burners up or down to get it. So fire resistance, how long does it survive this red curve? Where reaction to fire is, does it promote flame spread and basically increase the intensity of fires? So now we can use that when we're starting to evaluate systems. And just as a matter of interest, let's see, I'm not sure on Zoom if you can do a show of hands. If you can, how many of you have had to deal with a shipping container structure? Anyone? I think you can show hands, put up your hand or do something. Let's see if anyone's alive out there. William. Okay, I hope you're doing well. Yep, so we've got one person in the audience, two, anyone else? Three, John Mayering. Okay, 3, 4. Okay, so a couple of you had to deal with shipping container fires. So there is a paper, quite a few more than I expected. Wow. These come up from time to time. We've got a master's thesis and a paper published on this. And so you have these basically giant steel boxes that can form houses and multi-story structures. And if done nicely, they can actually look quite reasonable. They're still industrial at the end of the day, but they're modular. You can have them pretty much ready and then shipped to site, especially with miners. The miners love these because you don't have any site work. So everything can be done off site and you just arrive and erect. So they quite like that. The main components is you've got a couple of steel columns, and those steel columns at the 4 corners are your load bearing elements. And they are designed to carry the vertical load. And you've got these loading blocks at the top and bottom that transmit the load. And then you've got these corrugated walls on the side. And then you've got a floor system consisting of some channels or some beams and some timber flooring, and then a steel roof as well. And it's basically a welded up steel box. Now, often what you'll do then to get fire resistance is you'll take your wall and you'll put some channels on. So there is your shipping container wall I'm showing with my laser pointer. And then you put a stud, and then you put boards each side, because it heats up too fast. Steel heats up really fast, got a very high conductivity. So what happens is you need some sort of passive protection board. And so you put a gypsum or calcium silicate or something one side and the other, and that keeps it cooler. That prevents the unexposed side from getting too hot. So for instance, the fire is on the top, and then you'll prevent the bottom from getting too hot. So you will then have a certain amount of passive protection, one or both sides, and you need to design that passive protection so that the unexposed face does not get more than 140 degrees above ambient. That's what's called an insulation criteria. And so you can see in this case 160, 20 degrees ambient plus 140. So at this point in time, failure had just occurred. And so, okay, that was a great configuration. So you can have different configurations of these depending on where there you go. You might have it on the walls, but you can also have fire in from the bottom. So if this is a cantilever, you could also need fire to be prevented from coming in from the bottom. So that's something that you need to be quite careful of. Now, if you run through the calcs, your main load-bearing elements are your corners, these corner columns. And so it's quite critical working out what is their temperature after certain amounts of time. So we've done that, working out what's the minimum and maximum temperature for different fire exposures. And based on that, you can actually work out what is the resultant capacity. So if it says a 12 mil gypsum board each time, how hot will it be? And you'll get something like this. This will be the temperatures. And from this, you can then say, well, this column now has 600 kilonewtons or 400 kilonewtons capacity. And so you can then do a rational design on your columns on how strong is this column at 60 minutes, with certain passive protection. Say, yes, you can go 6 stories or 8 stories. It can still carry the load required with, after an hour or 2 hours fire exposure. And so, for instance, this would be the capacity versus time if you've got a 10 mil board or 20 mil board protecting it. So if it's unprotected, the capacity drops very fast. You're not going to get a 30-minute rating. If you've got, for instance, a 10 mil board, unprotected fails very quickly. There's your 10 mil board, the green, and then you can see it lasts a bit longer, then the capacity starts dropping, or 20 mil board, the blue, it lasts quite a bit longer. So depending on what capacity you need, you can then get it. Now, these structures are actually incredibly strong. The way they've been designed is, they get stacked very, very high on shipping containers, and they carry very high loads. So there's actually an enormous amount of capacity in them. So that's good. Also, they're welded together, so they really prevent flame and smoke from escaping. So they're very good integrity resistance, integrity preventing smoke and flame transmission. The real issue, though, with them is that you can get a standard fire resistance quite easy, because standard fire resistance don't really look at your connections. But in reality, in a real fire in a real building, your danger actually comes at your column, because you've got 2 items right next to each other. And if you find that, let's say there's a fire in one and not in the other, the red one here will heat up, the white one won't. And so at this interface, you have differential thermal movement, and these can create enormous forces. And if they are tightly linked together, it'll actually shear that connection. So that's something that may need to be considered depending on how you connect it. If it's a sliding connection, you're probably fine. But if it's welded, you're going to have a problem with shearing through against it. So some final notes. Apologies. Integrity resistance of containers is good. Insulation resistance requires boarding. Structural resistance can be achieved for load-bearing columns if temperatures are kept lower with passive protection. Restrained thermal expansion is likely to be the most dangerous failure mechanism. So that's something you'd need to look at and then think about when it comes to these sort of systems. Now, moving on to mass timber, and I'm really giving you a crash course in a couple of topics, so hopefully it's useful for you for the future. Now, mass timber is growing fast, especially Europe, America. There's a big emergence of that. We've got a couple of projects at Stellenbosch. We've got 3 PhDs and 2 master's students working on mass timber structures. And you see a lot of discussion regarding them. I mean, from an environmental perspective, really being promoted, and high-rise timber go. Oh, apologies, I've just forgot to kill the audio on this slide. So now what you find with these is that you've got to also be careful of who you listen to, because I think on the one hand, you can find people who are scared of the fire resistance and chuck it out the window altogether. No, you can't do this. Just plain and simple, it's combustible. You shouldn't be building structures, kind of the one resistance on the one extreme. On the other hand, I think possibly we are pushing the limits a little bit too far. And, especially with high rise, there's a lot of complexity. If a fire breaks out, you need a lot of things in place in terms of suppression systems, etc. And if your sprinkler doesn't kick in, you could have a lot of trouble. So you need to make sure that a lot of systems are really working together. And there's a couple of things that haven't quite been figured out in terms of fire resistance, connections, etc. So I'd say either extremes are not necessarily helpful, but we will see a rise. We've seen proposals for South Africa for 7 stories, 5 stories, etc. How well they'll get through council, I'm not sure yet, but there's definitely a drive towards this. And just as sort of a 101, timber 101, you've got multi-story housing, low-rise buildings. You've got your post and beam systems, which low-rise buildings, single-family homes, multi-story, where your mass timber are large, solid wood panels for walls, floors, roof. And most of the research in fire resistance is around mass timber. We've got big, chunky beam slabs, columns, etc., that you can design. And so this is your heavy timber systems. And this is more your light systems, where this is more thin pieces that are clad. Now, so one of the things with timber, it's quite a lot faster, less workers on site, construction, traffic, lighter weight of materials, etc., occupant well-being, reduced carbon footprint. However, you do also see one thing that is being flagged is safety during construction, and that is going to be an ongoing thing that needs to be dealt with, is that often the fire safety systems that you need, your sprinklers, your passive protection, your boards, detection, etc., that is only ready towards the end of a project. So during the construction phase, you can have large volumes of, or large areas of unexposed timber, exposed timber, which leads to a much higher fire risk. So if a fire breaks out in a timber building under construction, you have to be very careful. That could lead to quite a large disaster. So fire safety on site and your flows become a big issue. Now, when it comes to these sorts of systems, you have a beam, column, slab, etc. And what you do is you expose on the outside, and it kind of gets eaten away. And we can design the residual cross-section to carry the load. So as long as, even if it has charred, it has burnt away, as long as what's left there is enough, that's fine. So this is the column. So this, what you're looking at, is the column that went there. And as long as that is sufficient, then you can say, yes, at the fire limit state, well, the accidental limit state, you still have enough capacity, because you reduce your structural loads for an accidental limit condition. So you often have a lot of extra capacity in your systems. So because what happens is, if you've got a piece of timber here, just a small piece, if you have a look at the mass versus temperature, initially you heat it up, and then when you get to about 100 degrees Celsius, the moisture is driven off as steam. So then you have dehydration. And then it continues, and then you've got pyrolysis. So pyrolysis is when you convert a solid into a gas, and the gas can then burn. So this is when you start emitting combustible gases, and then they can now ignite. And then you've got char oxidation. So now you've got a char material that forms. So almost a protection layer as well, though it's a low conductivity layer. So how does this affect the strength of extraction? How does it affect compartment fire dynamics? Because the char protects it, but the pyrolysis gases will increase your fire severity. So now if you have a look at a big beam, so now let's say this is a glulam beam. So you've got a bunch of layers. You basically just glue the layers together. You can then machine it, etc. You've got a fire. It'll then char, and then you've got a charring front, and then you also have a heated layer where the temperature drops, but also what you find is you lose some amount of strength there. So this layer here is weakened. So for instance, I'm not going to go through all the ins and out details of this, but this is just as a group of structural engineers, so you can see what would a typical calculation look like. And this is quite simplified. We've left off zero strength layers and some other things. So for instance, a glulam beam, which is produced from SA pines used in the building, it's 130 wide, 720 deep. It's exposed to fire from 3 sides, so it must have a floor on top. And after 1 hour of fire exposure, what are the remaining dimensions? What remaining dimensions can be used for structural calculations? So based on the density, you get what's called a notional charring rate, and that's how fast the char layer proceeds through it. And so, for instance, after 60 minutes, you've lost 42 moles all around. Now, so your resultant width of the beam is about 46. And so you can then also see you've only got about 46 mils left, but you've got about 678 mils in height. And then determine the remaining dimensions for the structural purpose. An effective char depth is calculated. And so you can get an effective char depth, et cetera, and then you get updated properties. But then also what you can do is calculate your zero strength layer, but you end up with a residual beam and say, is that residual beam strong enough? Is that with reduced load sufficient to carry my loads? Yes, no. Okay, it has a 30, 60, 120-minute rating. And normally for 120-minute ratings, you actually need to start passively protecting it, boxing it out, doing other things, or you just need to end up with a very big beam to get that fire rating. One of the problems you can get with systems is that as they heat up and as the fire progresses, pieces can fall off. So for instance, this is what's called a cross-laminated timber. So there's layers running one way and layers running the other way, and it's all glued and pressed together. As it burns, pieces can fall off. So it doesn't all magically stay stuck the whole time. You do get char fall-off, and you can see then with pine or eucalyptus or different materials, you can still get a fire rating. So for this one, we got a 60-minute rating, and I think for the eucalyptus, we got 90, but it's still, that does influence the fire rating to some extent. When does the glue come off? And there are different types of glues, with some perform better. And unfortunately, normally the better performing glues are normally your ones that are more difficult to work with and potentially carcinogenic, where the ones that are easier to work with and cheaper, they tend to melt easier. So there's a lot of glue and adhesive research going on, but you do have to look at what adhesive you look for from it. But in mass timber, the real risk is down to your connectors. And we've got a student, Marika Duplessis, she's wrapping up her PhD on timber connections. And you have to be really careful with these animals, because if the fire gets in here, your aluminium or your steel heats up fast. And once it loses capacity, you have catastrophic failure. So connection failure is really dangerous and something you have to look out for. You can put in what's these sealants, intumescents, and these can close up your joints, because there's always a little bit of a gap that forms between your beam and column. So you can use it to seal. And the Eurocode sort of implies that you don't necessarily need this, but in our opinion, you should rather go for this, because it gives you a lot more tolerance and it provides a lot more protection to your system. Now, once again, there's the difference between fire resistance and a reaction to fire. Your timber buildings let's say now the building needs a 60-minute fire rating. Then the skeleton, and your building is now timber. You'll actually find that your skeleton, your floors contribute to the fire load. So your fire will last longer and be more intense. And then you may need to start asking, well, the code says 60, but because my structure is combustible, do I actually need a 90-minute fire rating now? Or do I need to clad a certain amount of these beams and columns to reduce the fire intensity? So those are guidelines and that research that's currently being addressed and being developed for this. So some final notes: fire ratings can be obtained. Timber chars is at a predictable rate, so you can use that. Connections are most likely reason for failure and collapse. Heat release rates and fire intensity increases due to the presence of exposed timber. Some codes limit the exposed area of timber. So that's something you'd need to be careful of. So we're going to move then on to these sorts of weird and wonderfuls. Now, what about an eco-brick home? So we've even heard of high-end homes where someone wants a green room added onto a house, or it's a big office park and they want to have this feature wall as you go in this green and friendly eco-brick wall system. And at this stage, you will have no idea where to start because there's just nothing in the codes to deal with, 2-liter Coke bottles filled with junk. And so for instance, in Guatemala, there's over 100 schools by one NGO, hundreds of homes. Are they fire safe? So a student of ours did investigations onto these and had a look at them. They're built in various ways. There might be a timber frame system within between, or a concrete frame system, and then you've got your ecobricks, and then you plaster them and clad them in. But basically, it's primarily plastic, maybe your polystyrenes, etc. So it's hydrocarbon. It's pretty much pure fuel. It just burns with toxic fumes. So you've got pure fuels, and you're encasing them in a wall. So you've got large volumes of petrol equivalent in a wall. So if you have a look at these, this was an assessment of the weights of different bottles. So they're a bit of a distribution, but somewhere probably between 400 and 600 grams. And the fuel content of these is basically between 0.4 and 0.6 liters of petrol per bottle. They are, as I said, pure hydrocarbons. And if you have it, the fuel loads that they produce, so the megajoules per kilogram, depending on what they're filled with, whether it's PVC or polyethylene, whether it's 400 grams, 600 grams, etc., and you build a little home, you could find that the fuel load in the bricks, depending on the arrangement, is higher than the fuel load of the home. So for instance, a residential home, that's the design fuel load. I think it's about 800 megajoules a kilogram. So that would be your design fuel load if you're going to do a performance-based design. Whereas the walls may contribute 2 or 3 times that. So you're pushing your fuel loads up hugely if the fire gets into the wall. If it doesn't, you're fine. If it does, you're screwed. So for instance, here is vertically orientated eco-brick walls with what's basically a plaster layer. So this is cob. So it is straw mixed with clay, and then you plaster it. If the cob layer holds out, you're probably fine. So in a low-risk structure, single-story, standalone dwelling, this is probably fine. But now let's say someone does this in an informal settlement. It's Mandela Day and a big corporate sponsors the construction of 500 homes, and now you've got a whole ton of these on top of each other. That where it becomes a problem, because once the fire gets into it, you can see lots of fuel, lots of poisonous gases being emitted, and you can also get flaming. So this is how you build them, though. You get your layers, you put in your cob, then you install your bottles, you put on a couple of scratch coats and all sorts of other stuff, and then you plaster it up, and you have a final flat wall, which can look very nice. But this is what a single bottle will look like when it's ignited. So exposed to a high heat source, it burns, and that's quite a flame coming up. And what also happens is there's flaming molten liquid that flows down. So it heats up, melts, and you can actually have a flow of molten plastic emerging from these, and that can flow across there. And the plastic itself as molten liquid can ignite. So that is also a consideration, which makes firefighting and spread a great challenge. So now here is a wall being tested, something ignited and coming through. So this is where the danger comes from having contained combustibles. And you can apply this principle to other things. So whenever you have insulation in a wall, and we do this all the time, we have a stud wall, a dry wall, and then we fill it with a material which burns pretty much the same. These nice expanded, fluffy insulation products, which are often plastic based. If the fire gets in there, it's going to run like hell and burn like hell. So insulation material and cavity walls is a major risk, because when and if the fire gets in there, it just rages straight through them. Now, so here you can see bricks being ignited. They also shrink and then flames emerge. But if you have a look at the front, you can see also now flames emerging from where the walls crack. And very beautiful pictures of, little flames coming out. So this was after the burners were turned off and then how the bottles were still flaming. And you can also imagine from the fire service perspective, if they arrive on site and one of these have burnt, it's extremely difficult to suppress because you've got all these little pockets. So you basically have to demolish to make sure all the fire's out. But there are other ways of doing this, if you want to now reuse waste plastic, so you can actually incorporate them. So this was research involving Resonate. Resonate is basically a concrete aggregate. So it looks like 5mm stone, and ranging from basically 0% to 50% plastic in a brick. So this is half plastic, this is 5 or 0% plastic. And you can see how the look gradually changes as you increase the plastic content. And if you expose these to high intensity heat, at low replacement values, 5 or 10%, you're probably fine. It's probably not going to do a lot of damage. But when you start getting to 20, 30, 40, 50%, what happens is that the plastic is heated, kind of squeezes out, and then it can ignite. And so these gases you see coming off are pyrolysis gases, and they can burn. And so your bricks could actually contribute to the fire severity and the production of noxious fumes. So depending on the structure, where this is, that may be dangerous or not dangerous. But if you've got large areas, especially if this was near evacuation routes, that could be problematic. So, and once again, this is at high replacement values, so you need to be careful. So this is sort of volumes of smoke coming off a single brick. Within 1 to 2 minutes under high intensity radiation, certainly it's emitting smoke, noxious fumes that you may need to then deal with and protect yourself from. And the bricks almost kind of char. The surface there gradually delaminates, and then this char front progresses further back. And you also have kind of a zero strength layer, and then there's your residual brick. So if it didn't influence life safety, this would probably be fine. You'd have to rip off the front and then reinstate, but maybe not. You can reuse the structure. I mean, especially if it was double brick, you'd probably be fine. You'd strip off the damaged bit, and then the back brick would at least still be hopefully low bearing. So, but you can see how different it goes from 5 to 50%, the sort of progressive increase in charring and the amount of plastic emitted. So this is reasonably low risk. This starts becoming a high risk. So these are sort of things that often architects, environmentalists, they want to do stuff, which is great, by all means, fantastic. But often fire risk is not considered. So ecobricks, fire ratings can be obtained. If you put enough plaster on, you can actually protect them and get a fire rating, a 30-minute rating possibly. Once bricks do catch fire, they're difficult to put out and contain large amounts of fuel, so they'll burn like hell for a long period once the fire slips into that void. If you've got bricks with plastic on the inside, furnace resistance, you can actually get quite a good rating out of them. Bricks release heat and will increase fire intensity in the same way that timber does. Further research needed. For low replacements of 10% or below, the risk is relatively low. For high, it's problematic. And also, if you plaster the bricks, if you have a plaster layer on top of the bricks, which is non-combustible, just a normal cement plaster, that'll also protect them and provide a lot better rating. Now, the last section I'm going to go on to is green facades. And this is really a crash course in all sorts of chaos and just thinking about how these things occur. So this is a building that's been proposed for Cape Town, and they're starting to become popular around the world, these green facades. I mean, they look very pretty. I mean, it'd be nice to live in a building like that. But think about in drought conditions, when water restrictions are enacted, plants may become very dry and readily combustible. So if this was now in downtown Cape Town and there are water restrictions saying you may not water your plants, you know for a fact you can't water the plants because everyone's looking at you. And if your plants are beautifully green, they'll know you're flouting those regulations. So they will die. And when they die, they're going to promote flame spread. So you are going to get fairly rapid flame spread over the surface. Vertical and lateral fire spread needs to be carefully considered. Because once again, if you come back to the National Building Regulations Act, not SANS 10400 Part T. SANS 10400 Part T is a prescriptive code that in theory should ensure compliance with the Act, but it's not obligatory. You don't have to stick to the guidance of the SANS codes. You have to stick to the requirements of the Act. And the Act says the spread of flame and smoke must be limited. There must be measures in place to detect fires and suppress fires. Now, if you have a look at this building, you could have flame spread across the whole building. So even if this was code compliant from a building code, because the building code doesn't, SANS 10400 Part T does not really address combustible facades, green facades. But the Act says you mustn't have flame spread throughout the building. You must limit flame and smoke spread. And so you can have a violation of the Act in a building which in theory is code compliant. And so, you know, flame spread across the outside could become a major problem. Also think about what are your plants growing in. And often with some of these systems, especially with the smaller plants, they're grown in little plastic, basically pots. So, and I showed you earlier how well plastic burns. So now you've got a whole bunch of these, and you may have these little plastic trenches or slots, and you may have pipes going to them to water them. So you can introduce a lot of fuel. And if you've got little plastic hoikies, you know, holding your plants and other materials, and this gets a bit dry, it's going to run like hell up the side of your building. And so that would be a violation of the Act. So Wojciech Wieruński, he's a guy in Poland, actually know him. He was posting some of the research he's been doing recently regarding green facades and testing, and they burnt different setups. And you can see it runs. When you have enough plants, especially when it's drier, the fire runs up it. And the contents, while the materials around the facade may influence, as once again, little pots or troughs, pipes, whatever it is, if you've got plastics and rubbers associated with these green facades, it may run. So as I said, most codes do not directly apply to the inclusion of large quantities of plants on a facade. Fire spread is likely to be influenced during dry conditions and depending on the plant type. Performance-based design and testing required. Plastic components add to fuel load and promote spread through voids, and then more research is needed. So this is going to be one of these things that I can see popping up as a problem in the future, where you've got a beautiful building which, you know, suddenly loses 5 floors due to a fire, and everyone runs around in circles. Oh, it was code compliant. Yeah, but you still get fire spread. So with emerging technologies, often our codes don't necessarily apply, and that's where you should go to performance-based design and understand the bigger picture. So yeah, so that's hopefully is giving you a bit of a summary of thinking about these different systems. I mean, we looked at shipping containers, which are non-combustible, fairly resilient structures, but you can modify them, cut holes in them, but you need to passively protect them, and then you can go high-rise. Connections are problems. Say timber, combustible, mass timber normally works out fairly well in fire, but once again, fire severity may be increased. Ecobricks are a risk. If the fire slips into the compartment, they're going to burn like hell. And you know, a plastic aggregate in a brick, relatively low risk, but at higher contents may be a problem. Most most resonate bricks are 5% or 10%. So they're probably okay. And then green facades, an emerging issue. I don't think we have enough research, but they are potentially a problem and could potentially promote flame spread on the outside of the building. So yeah, that's going to take me to the end of my presentation.